Today we're going to take a look at section 4.1, which is called Antiderivatives. And really quickly, before we move into antiderivatives, the first thing I would like for you to do, hopefully you have some notes with you. It doesn't look like anybody does. Do you have your notes? Kaylee does. Okay, so what I'd like for you to do, whether you have your notes or not, is we're going to write down derivative rules. So I'm going to be quiet for just a couple of minutes, and I'd like for you to write down what you believe the derivative is for each one of these. This is chapter 2 stuff, right? There's 2 slides of these before we move into the next part, okay? So I'm just going to be quiet and let you write down what you believe the derivative is for each of these 5 different functions. When you are done with this slide, if you just put your pencil down so I'll know when to flip to the next one, that'd be great. Pen or pencil, whatever you like, Mike. There's a few more on the next slide, and then we'll go back and we'll get them all written down. Your trig rules. Remember what all the derivatives were for the 6 trig functions. I hope so. We're just going to start on this slide and then we'll go backwards. So let's see what we remember. What's the derivative of sine? Cosine. Hopefully you're using some good notation with some prime notation here. So this is cosine of x, right? What's the derivative of cosine of x? Negative sine x. Lovely. What's the derivative of tangent?
Secant squared of x.
Yeah, good. Secant squared of x. And what's the derivative of secant of x? Lovely. Derivative of cotangent? Close. Negative, yeah, that's the part missing. So negative cosecant squared of x. And then the derivative of cosecant of x?
Negative cosecant x times cotangent.
Awesome. And we've talked about how all the have derivatives that have negatives involved. One way to remember. These also seem to sort of occur in pairs, very nicely. So like secant and cosecant derivatives have the same form, things like that. Okay, let's go back to the previous slide. What's the derivative of a constant function, like y equals b? What is it? It's 0. How about a linear function?
It'll just be A.
Yeah, it's just the slope of it, which is a. What happens when you have a constant multiplier?
The constant stays. You just take the derivative of f of x.
Good. Kaylee's helping me out. What about this side of the room? You guys have some ideas? What about the next one? Sums and differences. What do you got, Katie?
It's the f prime of x
Mhm.
minus 2 prime of
Right. We've been doing these, right? So you guys have been applying that, exactly. And Cameron, what'd you put down for the power rule one? Fabulous. Okay, so here's what we're going to be doing now. We're going to be starting with functions that look like what's on the right-hand side, and we're going to be going back to the left-hand side. That's really what we're doing, okay? Now, a bit of notation. You'll notice that when we moved from left to right on this screen, we started with y and we turned it into y prime, all right? So we need some kind of a notation that goes backwards, but typically we don't start with something that says y prime. Makes sense? It's just a function, and we're trying to go backward. So the notation actually looks like you're starting with y, and what will happen is it will turn into a capital letter. So maybe it's easier to think about lowercase f of x, and it turns into a capital F of x. So notationally, my lowercase letters are going to become capital letters when I move backwards into antiderivatives. So if you'll flip over to page 2, if you've printed these out, we're going to find a set of derivatives. Now, they're still written from left to right, but in your mind, you're thinking I'm going backwards. Okay, so all of these start out saying lowercase y equals. So my antiderivatives will all say they're capital Y equals. All right. So first of all, when we got a derivative of 0, what did the original function look like that made that happen? It was just a constant. And for what we're doing right here, typically we write our constants as the letter C, because C starts with, constant starts with C. So you'll see C used a lot. But you could use any letter. It really wouldn't matter. Don't use X and Y. That would be terrible. But any other letter would really be okay. So you'll see C's used a lot. So look at Y equals K. K is just a number. So when did we get Y, a derivative, to be equal to just a number? When did that happen? Right, when there was a variable to power 1, it was a linear function. So in particular, that k would have been multiplied by that variable with a power 1, which would be x. There's one caveat to this, is that there could have been another constant on the end of this. Because what's the derivative of that c? Well, 0, right? So every time I'm finding an antiderivative, these are actually called general antiderivatives. Because the reality is that any time I have that plus c involved in a function and I take the derivative, it just disappears. So to put it back in, I don't know exactly where it goes. And if you think about it, it really kind of makes sense, and here's why. When we're finding derivatives, we're talking about slopes, right? What does the graph look like as it's increasing and decreasing? That's what a derivative does for us. So if I were to take that same graph and I were to shift it up or down, like the image is the same, it's just shifted up or down, it doesn't change slopes, does it? The increasing, decreasing part didn't change. It's just where it crossed the y-axis, the x-axis, those values changed. So that plus c on the end is actually just a vertical shift. Vertical shifts don't change the slopes of functions. So that's what's going on from a graphical perspective. So the kicker is, and you can write yourself a note here, is that we always put plus c. Every time I do an antiderivative, I'm going to put plus c, plus c, plus c. So typically when people take my antiderivative gateway, which you guys will do shortly, when you take the antiderivative gateway, I have a lot of people who will write on the top of it, put plus c to remind themselves, put the plus c, put the plus c. I actually had one semester, it's been a really long time ago, where I had a really sharp student. He got every antiderivative right, every single one. He got a 0 because he didn't put plus c on anything. Obviously, he came in, he was able to fix it really quickly and retake it. But yeah, I mean, we don't want you to not get your points because you didn't put the plus c. So, all right, let's take a look at the next ones of these. What do you think is going to happen when we have a constant times a function?
Goes to the exponent rule, isn't it?
This isn't an exponent rule. That's the bottom one right here. This one will be an exponent rule. But what do you think is going to happen when we simply have, what did we do when we had a constant times a derivative? Like when we did derivatives with constants in them? Yeah, the constant just sort of comes along for the ride, right? And antiderivatives work the same way. Numbers that are multiplied, constant multipliers, they don't affect the value except in the fact that they're multiplied by them and they're multiplied by the results. So when we do the antiderivative here as well, we have that same k, and then we have the capital F of x, and then we still have that plus c. Okay, so we take the antiderivative of the part with the variable in it. What would you guess is going to happen when I have sums and differences? Yeah, I mean, they're exactly going to become the sum and difference of the individual pieces. So we have capital F of x plus or minus capital G of x, and then we still have, of course, the plus c on the end. All right, the last one is the most interesting on this screen, I mean. So it says, what's going to happen when I have a power? Well, let's talk about what happened when I took derivatives of powers. So somebody tell me what happened to the n when I took the derivative of x to the n before. Yeah, it decreased by 1. So the exponent decreased by 1. So we're going to do everything in the opposite fashion. So what do you suppose the exponent's going to do this time? It's going to increase by 1. Okay? Before it decreased, now it's going to increase. What happened to the n when I took the derivative? Because something else happened too. Yeah, it made itself a coefficient, right? It became multiplied by what I did. So if multiplying was what I did before, what do you suppose is going to happen this time? Division, you bet. So this is going to be division. One more time before I write it in of what I'm dividing by. Previously, what I divided by or multiplied by was the previous exponent. This time, it will be that plus 1 exponent. And if you think about this, like let's say you tried to take the derivative of this now, right? Use your derivative rules to take the derivative. Well, we'd take the n plus 1 down. That n plus 1 that I brought down would cancel at the denominator. And the degree would become 1 less, which would make it a degree of n. So it would, in fact, get you back over here where you began if you took the derivative. And I'm missing one thing, plus c. Okay, so those are my power rules. There is a caveat to this. It's written in the notes, but it doesn't say it here. This n cannot equal -1 in order for this to work. And you might be saying, well, what if it did equal -1? Well, then you'd be in Calc 2. We talk about what happens when there's a -1 exponent in Calc 2. There's a different rule that's applicable, but it simply does. It works for anything else, just not -1. It doesn't make sense. Obviously, if it's 0, it becomes one of these other functions as well. It's irrelevant. But any other non-0 and non-1 exponent, this power rule will work this way. Okay, you want to take a look at trig? So here's the interesting thing about trig. When you take a look at these trig pieces right here, what they really are is they're really just this screen flipped, okay? So you might say, okay, but what if I want the antiderivative of tangent? We'll get there, okay? It's just not this section. There's another section later on where we're going to catch those. Yes?
Negatives.
No, they don't. You're right. And so the negatives will get inserted as we do it the other direction. You're right. They don't have negatives, so when we take the antiderivative, the negative will show up. Yeah. So I'll address that when we get there. Let's actually do the first one. It actually ends up giving us that. So if the derivative of sine is cosine, and the derivative of cosine is negative sine, it would be negative cosine. So I'm going backwards to cosine, and the sign has to switch. And if you think about moving the other direction, what's the derivative of cosine? Well, the derivative of cosine is negative sine. The negative would cancel with the negative that's written here beside the cosine, and I'd be getting back to sine. So
You're doing all the same thing, but whatever was positive for your derivatives is now negative.
that's exactly right. You're doing just the same thing in terms of turning it around, but your signs are actually doing sort of the opposite of what they were before. Mm-hmm. So what would the antiderivative of cosine be? That would be sine of x plus my c. All right, how about secant squared? Yep, that's tangent, and there's no sign changes on that one, so that's nice. How about secant tangent? That's secant, again, moving backwards. No sign changes, so that's a plus c. These last two, where I would start with cosecant squared and cosecant cotangent, will both end up being negatives, right? So I have a negative on this one, and I have a negative on the next one. What's the antiderivative of cosecant squared? That would be the negative of the cotangent, right? Make sure you got your plus c's and everything. And then the antiderivative of cosecant cotangent. That's cosecant. plus a z. All right, is that good for everybody? Okay, so you're going to be encountering, let me find out when it is so that I don't misspeak, an antiderivative gateway on this soon. Do I not have it in here? Oh, November 11th, so a week from Monday. So we're going to practice and make sure that we're really good at this for a few class periods. But it is coming up, so you've got just a little over a week before you're going to do a gateway quiz for this. And remember, gateway quizzes have extra credit attached if you finish them the first time. So this is another opportunity for an extra 5 bonus points, okay? All right, so what we're going to do for the rest of this material is simply take antiderivatives. All right, just like with the derivative quiz before, on a derivative quiz, right, the gateway, you're not going to simplify anything for your homework for tests and quizzes and things in class, you will. So we're going to simplify pieces, but I'll also just remind you, you could stop here if we were doing the gateway as a reminder. All right, so everything works in reverse. Oh, and I haven't actually shown you this notation. Let me actually do that first. This notation right here means find general antiderivative, okay? It's kind of like saying find f prime. If somebody wrote in the directions find f prime, you'd know I'm taking a derivative. Well, this notation with the script s means find the antiderivative. The other thing is that this at the beginning and this at the end are rather attached. They're kind of like the beginning and the end of a parentheses. What you're taking the antiderivative of is what's sandwiched in between. So you might say, well, what does the dx mean? And it does actually have a meaning. This notation at the beginning means take the antiderivative. The dx at the end means that the variable you're taking the antiderivative of is x. And you might be thinking, well, of course it is. The reality is that calculus continues beyond Calc 1, and Calc 3 actually encounters multivariable calculus, which means you have x's and y's and maybe z's or other things involved. And so if you want to take an antiderivative, you have to know what the variable is that you're working with. So that's why that notation's occurring. I'm not saying that to scare you. I just want you to know that's why it's there. It is really there for a reason. It just doesn't really kind of matter to us in Calc 1. We're just going to make sure we're clean and clear and we're doing the process with the right notation, okay? So the s at the beginning, the dx at the end mean find the antiderivative with respect to x. And once I do that, both of those pieces go away. It's kind of like the parentheses. Once you actually distribute through the parentheses, you don't keep writing the parentheses, right? Once I take the antiderivative, I don't keep writing the s at the beginning and the dx at the end. They disappear as well. Sound good? All right. So what we're going to do is piece by piece work through these because these are sums and differences. So this is like that sum difference one that we saw earlier. So what would the antiderivative of 2x be? It would be x squared. All right, so the 2 at the beginning sort of gets pulled back up to the exponent. And if you weren't sure, and you were like, well, I don't know, what would I do? What if it weren't a 2 at the beginning, right? Like, what would I do then? Well, let me show you how you could think about it. This is x to the 1, right? So if I add 1 to the power, that becomes x squared. I shouldn't have another pen mix this up. Okay. And the 2 would be here at the beginning, and then I would divide by the new power. All right, the 2 is the constant multiplier, it stays. My exponent increases by 1, and then I divide by the new exponent. But do you see what happens with the coefficient of 2 and the denominator of 2? They're going to cancel, whether you realize it from the beginning, like Nick did, or whether you do it from this perspective after you've done these pieces, they'll still cancel either way, okay? The other piece is 3x squared. So let's actually do that from that perspective. This 2, well, hang on, it's a negative, yeah. The 3 is a constant multiplier, so it stays. The 2 as a power will increase to a 3, and then I will divide by my new power, which is 3. And then what do I need to put at the very end? Plus c. So if you were working on the gateway, you could actually leave it like this, and that would be totally fine. When we're working on homeworks and things like that, we'll simplify what we can. And, of course, pieces of this do simplify, the 2's and the 3's in particular here, clean up very nicely. So this is actually x squared minus x cubed plus c. How could you check your work?
Take the derivative.
You could take the derivative, right? If you take the derivative and it gets you back where you were, then you've done it right. You don't even need a back of the book. You don't even need WebAssign to sort of give you that thumbs up, that little green check. You don't need it. You can take the derivative and you can find out if you did it right. Is that problem okay? Yeah? All right. Let's try the next one. Just like when we were doing derivatives, you'll notice that anything with a denominator, we don't have a rule for that, right? Like there's not a concrete rule that says, if you have a denominator, do this. So when we see denominators, what we want to do is rewrite them in a way that they don't exist, right? Moving things around so that the denominator pieces come up. So how could I rewrite this so that I don't have the x to the 6th in the denominator? Yeah, I can make it x to the negative 6. Absolutely. And once I get it in that fashion, it looks like one of the antiderivative rules that we have. So it's a power rule, right? So what will I do for its antiderivative? What's the power rule over here say to do? Add 1. Now, it's negative, so you need to be a little bit careful. I'll actually write it down that way. So negative 6 plus 1 divided by negative 6 plus 1. Every now and then I have people who like to actually write it that way on the gateway, just in case they accidentally did a subtraction wrong. They don't want to make that mistake to cost them on the gateway, or, it's okay. How about the 2? That would be the derivative, but I want the antiderivative. So it would be 2x. I reattach the x when I go backwards. Yeah, very common thing to go backwards on those two. And then I need plus c. Again, this is perfectly acceptable for the gateway, but negative 6 plus 1, that's 5th to 6th grade stuff, so I know you guys can do it. Sometimes we all make mistakes sometimes with it, I get that. But I know you can. So what is negative 6 plus 1? It's negative 5, yeah. So this is x to the negative 5 over negative 5. Minus 2x plus c. Again, this isn't quite finished because I want my function to look the way that it began when I began the problem. When I began the problem, I didn't have a negative exponent on x, right? It was actually in the denominator, so I want to put that back into the denominator. So I want to have the 1 on top. That negative 5 that's on the bottom can still be on the bottom, and it's just going to be joined by the x to the 5th. So it ends up looking like that. Is that all right? Yeah? Okay. More of the same. As much as anything, the examples that I chose are because I want to make sure that you can remember and think through how we rewrite things to make use of the rules we have. So any ideas about how to rewrite this 1 over x square root x in order to make use of the rules that we have? Okay, so you're bringing them up pieces at a time, which you can do, x to the negative 1 and x to the negative 1.5. Because they're multiplied, I can do that. If it were added, we couldn't do that, but they're multiplied, so that's true. What else could you do then? Because I don't like both of them sitting side by side. Right. We can combine them. That is a power or an exponent rule, property of exponents. Negative 1 and negative 1/2 is negative 1 and 1/2, which is negative 3/2. The other thing you could do is you could have done it in the denominator and then moved it up. Instead of moving them up in pieces, while they're down here, you could have thought through it that way. This is x to the 1/2, right, in the denominator. So this is x to the 3/2 in the denominator, and then moved it up as a negative. Just switching the order of what we're doing, ending in the same place, of course. All right. So it's actually in the right form, well, not the right form, but in a form that has a rule that we've actually learned. It's a power rule. So what will I do to the negative 3/2 when I take the antiderivative? I'll add 1. And again, I'm going to write it out just to make sure everybody's okay. Adding 1 to the power, and I'm dividing by that new power. Plus c. Gateway, that's it. Not a gateway, we keep going. So what do we get? Well, what is negative 3/2 plus 1? It's negative 1/2. So this is x to the negative 1/2 on top, negative 1/2 on bottom, plus c. There's actually 2 problems with the way that this is notated. Somebody give me one of them. We got a fraction in the denominator, so fractions inside of fractions are not okay. What else is a problem? I have a negative exponent, so I have to deal with both of those pieces of information, all right? Since Nick mentioned the fraction in the denominator first, let's actually deal with that one first. How do I change this so that I don't have a fraction in the denominator? I multiply by the reciprocal, which is negative 2 in this case, right? Yeah, so I'm going to actually rewrite this as negative 2x to the negative 1/2. Right, that's the reciprocal. All right, everybody good with that step? And then Jeffrey mentioned the power being negative. So I need to pull that back into the denominator to make it positive, right? But it's also fraction, and it didn't start out that way either. So we'll change it to a square root. So this will be negative 2. It will be a square root because that's what 1/2 does. And it's positive 1/2 in the denominator because it was negative 1/2 in the numerator. So we end up with this as our antiderivative. You might notice that I'm not writing those capital Y equals here, right? If it makes you feel better, it's not that you can't. You certainly can. The reason that it's not necessary is because it doesn't identify this as little y equals. It's actually giving you the script s and the dx at the end, and you're sort of just making an equivalent statement afterwards. So that's why that's happening, and I'm not using any notation. Beyond that, it's because of the notation that it began with. All right, so what do you think is going to happen when you have a product? Oh, and we would love to do the product rule in its opposite form, but that would be something in Chapter 5 that we're not going to get to this year. Darn, man, what? Yeah. Yeah, you're exactly right. So the only thing at our disposal, and this is part of why antiderivatives in Calc 1 are so nice, is because there's no product rule, there's no quotient rule, and there's no chain rule. All right, we have a very minor additional rule that we'll add at the very end of this chapter that will encounter a little bit of product rule, quotient rule, chain rule stuff, but only from a very, very tiny perspective. It doesn't encompass everything. So that's why antiderivatives are friendlier, is because we have less to work with. So we have to FOIL it out. And when we do, then we'll have pieces that will be something we can take derivatives of. So when we FOIL this out, I'm going to have 3x squared. On the inside, I have 3x, and on the outside, I have negative 2x. This is plus x. And then my last two pieces are negative 2. Oops. dx. Okay, is that okay? Combine like terms and all that jazz. All right. What's the antiderivative of 3x squared? That's x cubed. Or you could write 3x cubed divided by 3, if that makes it clearer for you. What is the antiderivative of x? That's part of it. X squared and then over 2. We've got to divide by the new power. And again, take the derivative of it, right? X squared over 2. You bring the 2 down, cancel the 2 denominator, so it would work. Oh, it's an addition. Thank you. My apologies. And then my negative 2 at the end. Yep, negative 2x and plus c. This doesn't even have any simplification. If you really don't like the 1/2, like the part that's got a 2 in the denominator, you could write 1/2 x squared. That would be okay too. It wouldn't hurt anything. But it's the same thing, right? It's not any better. Any questions on that one? So there's algebra still, right? Still got to do our algebra sometimes. Trig. Look at the trig. Okay. The first piece is a pretty direct application of what we've been doing, actually. The 1 at the beginning. What's the antiderivative of 1? That's x. Now we have the negative cosecant x cotangent x. Well, that's actually positive cosecant of x plus my c. Is that okay? The negative is actually in the problem, right? So I end up with a positive cosecant when I go backwards. 6 is not quite so direct. There's definitely a division here, without question, right? And what happens when I encounter some of these trig pieces that don't look like what I need is I have to use some basic trig identities. So what do I mean when I say basic trig identities? There's not very many of them that I would consider basic, first of all. So jot yourself down a list, write these down. You should know the reciprocal identities. Right, so reciprocal identities, I'll say what they are, but you can print, I have a handout online in our classroom of trig identities if you want to print them out. The reciprocal identities are that sine is 1 over cosecant. Cosecant is 1 over sine. Cosine is 1 over secant. secant is 1 over cosine, and tangent is 1 over cotangent, and cotangent is 1 over tangent. Those are the reciprocal identities. It's the way you flip them, okay? So that's reciprocal identities. You need to know the quotient identities. The quotient identities are that I didn't say that right. Tangent is sine over cosine, and cotangent is cosine over sine. Because you should know quotient identities. There's only 2 of them. And then the last one is Pythagorean identities. And there's 3 Pythagorean identities. The one that you're most familiar with probably is that sine squared plus cosine squared equals 1. Okay. There's 2 more versions that involve tangent squared and secant squared. And I'll let you get those because I always get the signs wrong when I say them out loud, so I'm not going to say them out loud. I'll undoubtedly say it wrong. But there's some signs involved in getting that done. So I bring this up because those are the ones that you should know. When they come up, they are considered basic trig identities. And there's one of them in this problem. The one that's in this problem occurs in this denominator. Now, it doesn't quite look like what I said, but it's a version of it. Yeah, Kaylee, why is it cosine squared of x?
Because you get 1 by doing cosine squared x plus sine squared x, and so you're just moving the 1 over, or the sine over.
Yeah.
with 1.
You're right. So this is the Pythagorean identity that we're referencing. And what Kaylee said, and she's exactly right, is that if you take the sine squared and you move it to the other side as a negative, you're going to have the denominator. Does everybody see that okay? Mind blown, I can just tell right now, that look on your face. But is it okay? Okay, it usually shows up like this. This is where you see stuff, is when you see it a lot of times with sines and cosines, anyway, when they use the Pythagorean identities. So that denominator is really just cosine squared. So I'm going to rewrite this this trig identity, or this piece of it with the trig identity, sine x over cosine squared of x. And it is squared, dx. Okay, so you might be looking at that and saying, okay, Dr. Hands, that's still a quotient. And you're right, it is. But cosine squared just means cosine times cosine, right? Okay, so I'm doing a manipulation. I'm going to cut this now. This is really just sine of x over cosine of x. Wow, that was bad. Cosine of x dx. It looks like there's a quotient. In reality, we're going to change it to look like there's a product in a moment. In particular, if I were to break it apart like this, what is sine over cosine? That's tangent. So this first piece here can be rewritten as tangent. Now, obviously, I can't just move cosine up there. I mean, it's in the denominator. It really is. But you can interpret and think about this like 1 over cosine. That's a reciprocal identity. What's 1 over cosine? That's secant. So in this one problem, we encountered a Pythagorean identity, a quotient identity, and a reciprocal identity. Those are the 3 basic types of identities that I just mentioned, aren't they? They are. They're really important, and they don't all occur, 3 at a time. Like that's kind of crazy that they all happened in this particular problem. But this is a good example to show how they show up. All right? And, of course, at this point, if you've done it correctly, you should end up with something that you know how to take the antiderivative of. It has to be one of the rules. We're very limited. We don't have that many rules to fall back on. What's the antiderivative of tangent secant?
Yeah, negative secant.
Close. It's not negative. Tangents and secants don't have any negatives involved. Only the cos do, remember? Okay. Yeah, so the antiderivative here is actually secant x plus c. That's it. The trig was the hard part of that problem. The calculus was super easy. It was the trig that caused all of the manipulation mess. All right. So there's a slight variation in the directions when we move into number 7. On 1 through 6, the phrase asked you to find the general antiderivative, and now this says particular solution instead. What does that mean? Well, what it means is that we are going to figure out what in the world the plus c on the end actually is. Is c 5? Is c 15? Is c 0? It could be. We're going to figure out what is c. And the only reason we're going to be able to do that is because if you'll notice, they give us one additional piece of information that we didn't have on those other problems. they actually give us an ordered pair. So what I talked about before is that plus C really means it's just shifted up and down. It's a vertical shift, right? But now they're actually telling you a point that it has to cross through, and once it fixes in a point, there's no more shifting. It has to go through that one particular location on the graph, and it fixes the C value. There's no more vertical shift available. So the process looks very similar. It just has an additional step at the end. So notice here on this one, it actually starts out telling you f prime of x equals. So if I take the antiderivative, it will be f, because it started out f prime. Right? It's moving from the right-hand side to the left-hand side of that very first derivatives screen that I did, the derivatives screen. All right, so what is the antiderivative of 4x squared?
4x cubed over 3.
And plus c. Okay, that's 4x cubed over 3 plus c. Okay, so that's actually the same thing we already did. The notation looks a little different because I didn't have the script s and the dx. I had an f prime, and I wrote it as f. Part of the reason that's the case, though, is because they're giving you this initial condition, and they want a little bit of notation to be able to do that at the end. So notice they tell you when x is -1, y is 3. So what that means is that over here, where I have the f of x, I get to evaluate that at 3. And where I have the x right here, that's -1. And the only thing then that still remains undetermined in this particular equation is c. So I can solve for c. So I have 3 here. -1 cubed is -1, so this is -4/3 plus c. And if I add the 4/3 to the other side, and I need to get a common denominator, so this is 9/3, right? So c, well, I'll just do it this way. C is equal to 9/3 plus 4/3, which is 13/3. The thing that you have to remember, and this is a common place where people just, you feel like you've achieved something. I found C and I can move on, is remember the goal is to actually write the equation. Just finding C was an intermediate step. I had to find C to do it, but now I want to come back up to the original equation, which was here, and I want to rewrite it with the appropriate C value that I just found plugged in. So 4x cubed over 3 plus 13 over 3. This is the particular solution given this initial condition, right? One piece of information in addition to the antiderivative I was supposed to find. Okay, one more problem. This one's a little bit different. Notice on this one, what am I originally given? The second derivative. Okay, but if I take the second derivative and I go back one step, where will I be? The first. So as I'm working through this, the process is the same. The notation just goes back a step. Before I would have got to the second derivative, I'd had to pass through the first derivative. So I have x squared. What is the antiderivative of x squared? Perfect. X cubed over 3 plus c. And they give us this initial condition about f prime. They tell us that when 0 is in for x, that I get 8 out for y. So if I were to evaluate this and put over here, I get my 8 out when I plug in right here, 0 for x. What's c? It happens to be 8. This one was very clean and easy to, because the zeros out. Zeros are wonderful. I love zeros. They're great. All right, so as I'm working through this, what happens now is that I need to take this original piece that I just found, like the f prime that I just found, and put the c back in right now. I can't just keep going. All right, I have to do it now. So this is f prime of x equals x cubed over 3 plus 8. And then I wash, rinse, repeat, like the shampoo bottles, right? Okay, so I do it again. So I went through, I found f prime using the same thing I just did on the previous slide with the previous problem. And now I'm going to do the same thing and I'm going to find f. So what is the antiderivative of x cubed over 3? Well, ignore the over 3 for a moment. What would I do with x cubed? It'd be x to the 4th. And I know that I'm going to need a denominator that's going to have 4 in it as well. But there's already a 3 down here. So it's now 4 times 3. 3 that was previously there, the 4 that's the new denominator because it's now x to the 4th. And then how about the 8?
Plus 8x.
Plus 8x plus c. So maybe you didn't need me to actually write out 3 times 4. You would have just as soon jumped into 12. We need it there eventually, right? So here's f of x. But I'm supposed to now be finding what is this c. And it might actually be a good idea, just to clarify, if I call this C2, right? It's the second c value. And I'll go back and I'll call the first one C1, just to say that they're certainly not the same. C being 8 before does not mean this c is also 8. They're just different constants, or at least potentially so. All right, so the other piece of information then that I was given, lovely enough, tells me that f of 0 is 4. Well, okay. So 4 here on the left, 0 for my x's. What does C2 end up being? Happens to be 4. Again, that doesn't always work out because I don't always get to insert zeros. I did on this one. And so my final answer then needs to be that function that I just found with the C2 event plugged in. So I will take this piece right here and rewrite. So I have f of x equals x to the 4th over 12 plus 8x plus 4. Any questions? Okay, one more heads up. I'm pretty sure, you can double check for me, but I'm pretty sure there's no more written homework assignment for the rest of the year. It's all WebAssigns. I know it's true for today because I see it in my notes, but I'm pretty sure that I actually noticed that earlier when I was looking through some things. So that I think there may be one more, but there's not for today. So you have WebAssign due on Monday for these antiderivatives, and then we will continue down this road with some more information about antiderivatives on Monday, and I'll have your test back then as well.